Welcome to This Explainer. I am absolutely thrilled to have you here today. Look, if you've ever opened up your organic chemistry notes and felt just a wave of immediate panic, you are in the exact right place. Today, we're taking a completely stress-free, step-by-step journey that's going to take you from absolute zero to absolute hero in understanding haloalkanes and haloarenes. Seriously, are you feeling like you're starting organic chemistry totally from scratch? Or maybe you kind of feel like your entire 11th grade chemistry foundation just evaporated into thin air? Well, I want to acknowledge that anxiety right now because it is so incredibly common. But I promise you, we are going to build everything from the ground up today. You really don't need to be an expert to follow along. Just stay with me, focus on the concepts we go through, and let's build that confidence together. Here is our super straightforward roadmap for today. We'll start with organic chemistry from scratch, then move into bonds, degrees, and hybridization. Classifying halo compounds, the art of naming, the nature of CX bonds, and finally, preparation and the grooves process. Okay, let's jump right into Section 1, Organic Chemistry from Scratch, the Foundation of Hydrocarbons. So what exactly are we studying today? By definition, haloalkanes and haloarenes are essentially chemical derivatives. It's actually pretty cool. Think of a simple hydrocarbon molecule, literally just carbon and hydrogen. If you pluck off one of those hydrogen atoms and just snap on a halogen atom instead, like fluorine, chlorine, bromine, or iodine, boom, you've just created an entirely new derivative. You've made a halo compound. Now, what's really interesting here is how visually simple the origin of these compounds actually is. Let's look at these two categories side by side. First, you have aliphatic hydrocarbons. These are your open chains, so think straight lines or little branches. Swap a hydrogen for a halogen there and you get a haloalkane. Simple, right? Now, on the other hand, we have aromatic hydrocarbons. These are your closed rings, most famously the benzene ring. Swap a hydrogen out of that ring for a halogen and you get a haloarene. It is literally that straightforward. Moving right along to Section 2, bonds, degrees, and hybridization, getting to know carbon intimately. To truly understand these molecules, we've got to zoom in a bit and understand exactly how carbon connects with its neighbors. You're going to hear the word hybridization thrown around a lot in chemistry, but honestly, here is the simple trick to master it. When carbon connects to another atom, the very first bond it makes is a strong single bond. We call that a sigma bond. Now, if it makes a double or triple bond, those extra bonds are pi bonds. So if you're trying to figure out hybridization, whether a carbon is sp3, sp2, or sp, you only count the sigma bonds and any lone pairs of electrons. You completely ignore the pi bonds. Seriously, just pretend they aren't there. It's just a simple counting game. And speaking of counting, I absolutely love this analogy for understanding the degree of a carbon atom. Think of carbon degrees like best friends. If a carbon is directly attached to only one other carbon, it has one best friend, say mummy, so it's a 1 degree or primary carbon. If it's attached directly to 2 other carbons, well, it has 2 best friends, mummy and papa, making it a 2 degree or secondary carbon. The degree is literally just a count of direct carbon-to-carbon friendships. Awesome! Let's head into Section 3, Classifying Halo Compounds, Organizing the Chemical Families. Celebrate for a second because you just got through the basics and you are now totally ready to categorize these molecules. Just like sorting out a giant family tree, chemists group these halogen compounds into distinct families based on where the halogens sit. Let's look at compounds that have 2 halogens. We call them dihalides. This is a massive classic exam concept, by the way. First, we have geminal dihalides. Think of the zodiac sign Gemini, meaning twins. In this case, both halogen twins are attached to the exact same carbon atom. Then we have vicinal dihalides. The word vicinal implies vicinity or neighbors. So here the halogens are attached to adjacent side-by-side carbon atoms. So remember, gem means same, vix means neighboring. And this brilliantly illustrates another absolutely vital way we classify them, by the hybridization of the carbon that's actually holding the halogen. Check this out. If the halogen sits on an sp3 hybridized carbon, meaning a carbon with only single bonds, but it happens to be right next to a double bond or a benzene ring, we call it allylic or benzylic. However, if the halogen is attached directly to a carbon that is actively making a double bond, an sp2 carbon, it belongs to the vinylic or aryl families. You've really got to pay close attention to exactly which carbon the halogen is touching. All right, let's look at Section 4, the art of naming, mastering IUPAC and common names.
Now that we know their families, we need to know what to actually call them. So let's shift gears to nomenclature. And look, I want you to completely reframe how you think about this. Do not think of naming as brute force memorization. Think of it as simply following a really logical set of instructions. Here is your universal 3-step naming sequence. Step 1, find the word root by counting the longest continuous carbon chain. 3 carbons, that's prop. 4, that's but. Step 2, look at the bonds between those carbons to find the primary suffix. Are they all single bonds? It ends in ane. A double bond? It ends in ene. And finally, step 3, at the very front, add your prefixes. If there's a chlorin, you write chloro, and you absolutely must include the number of the carbon it's attached to. Always number your chain so the halogen or the double bond gets the lowest possible number.
While we're on the topic of naming things, we have to talk about isomers. Isomers are simply molecules that have the exact same ingredients, meaning the same molecular formula, but a totally different arrangement. Chain isomerism means the actual length of the main carbon chain changes. So maybe it goes from a straight 4-carbon line to a branched 3-carbon chain. On the flip side, positional isomerism means the main chain stays exactly the same, but the halogen just packs up its bags and moves to a completely different carbon spot. So again, same exact ingredients, entirely different recipe.
Section 5. The nature of CX bonds. Electronegativity and bond trends.
Okay, let's transition from how these molecules look to how they physically behave in the real world. The carbon-halogen bond, the CX bond, is truly the beating heart of this explainer, and it's all about halogens acting like incredibly powerful electron magnets. Imagine sliding down the 17th column of the periodic table, right? From fluorine down through chlorine, bromine, and finally iodine. As we move down, the physical size of the halogen atom gets larger and larger. Because the atom is bigger, the physical distance, the bond length between the carbon and the halogen also increases. But here's the massive catch. As size increases, electronegativity, which is that atom's power to pull negative electrons toward itself, actually decreases.
Now, you might be wondering, why does that matter for breaking bonds? Well, let me share this fantastic analogy from our source material, the samosa party. Imagine a teacher and a group of students. A student standing right next to the teacher is highly supervised, right? It is going to take immense energy and a lot of convincing to pull them away to a samosa party happening outside. But a student standing way in the back of the room, super far away from the teacher, give them a quick nod and they'll easily break away to go grab a samosa. Let's connect that samosa party directly to bond dissociation energy, which is just the energy required to snap a bond in half. Fluorine is that tiny student standing right next to the carbon teacher. It's small, the bond is incredibly short, and the attraction is fierce. Breaking a CF bond requires immense energy. Iodine, on the other hand, is a massive atom standing way far away. That CI bond is long and relatively weak, meaning it breaks very, very easily. So, the crucial point we need to take away here is a massive exam alert. Because electronegativity drops as we go down the table, you'd naturally assume that tiny, highly electronegative fluorine creates the strongest dipole moment. But it doesn't. No way. Because of something called electron gain enthalpy, chlorine actually edges it out. The carbon-chlorine bond has a higher dipole moment than the carbon-fluorine bond. Do not let this exception trick you. Mark it in your brain for sure. And finally, Section 6, Preparation and the Grooves Process. Synthesizing alkyl halides.
Fantastic. We know what they are, we've named them, and we know exactly how their bonds behave. Our final step today is learning how to actually create them. It's time to put on our lab coats and synthesize some alkyl halides. There are 3 primary methods in our toolkit to bring haloalkanes into existence. You can build them from alcohols, you can make them directly from hydrocarbons, or you can swap one halogen for another in a halogen exchange reaction. Today, we're going to focus our attention completely on that very first, incredibly important method, starting with alcohols. This brings us to a specific and frankly quite famous technique called the grooves process. Here's how it works. You take a primary or secondary alcohol and you react it with what's known as Lucas reagent. That's just a mixture of hydrochloric acid and anhydrous zinc chloride. The zinc chloride acts as a really clever dehydrating agent. It basically reaches in, pulls out the oxygen and hydrogen from the alcohol to form a water molecule, and brilliantly substitutes the chlorine right into its place. The water's removed and an alkyl chloride is perfectly synthesized. It's a beautiful reaction. And just like that, we've reached the end. Look at what we just did. You've completely mastered the fundamental building blocks, mapped out the bonds, named the structures, and successfully synthesized your very first alkyl halides. You literally went from 0 to hero. But here's the thing. Now that you have these powerful, halogen-loaded molecules in your toolkit, how are they going to react when we unleash them onto the rest of the chemical world? Well, that explosive question is exactly what you'll discover in the next chapter. Thank you so much for joining me on this explainer. Stay curious and keep learning.